Um, uh, we will talk about physics of NMR, basic physics of NMR. Of course, there will be some sort of chemistry will be there. Why we need a chemistry? Because though NMR spectrometer is being invented by physicists, it's been extensively used by organic chemistry and inorganic chemistry. So it is good to know that what they are using, and from that perspective we can understand that much better way than as a physicist. So I would give you some results, some information about NMR results on solution state. Also we will go for a solid state NMR as well. So I split into two part. One is a instrumentation with solution NMR, and complete solid state experiments and results. So you can stop me at any time. I would like to give you complete information of physics of NMR, I would say, from my understanding. So why we need a NMR? So that's the first question to be asked. So the technology breakthrough at present, you people could have been listened that what is quantum computer. So the first demonstration of qubits with experimental is done by using NMR. So it is good to tell that this is the time to stood up and learn NMR spectroscopy. What else you can do with NMR? NMR you can use for chemistry, biochemistry, medicine, pharmaceutical industry, of course, physics, material science, of course, food sciences, environmental sciences, petroleum industry. And people are now exploring to apply to the many other divisions like what you say, our security perspective, and in military and aerospace, something like that. People are start exploring that whether we can use the NMR spectrometer to those areas. But this technique has been already developed over you can say that 50 decades, more than 50 decades. So the very first NMR thing has been happened by theory in 1938, where the Rabi oscillation, two atomic oscillation, is the first thing the NMR has been found out. So 1946, NMR first NMR signal was recorded by Carl Purcell and Bloch, and from that point, no, we are in a different dimension. There is no field is exceptional without NMR, I would say. All the field you can apply this NMR spectrometer in different form, not in one form. So that is what this old talk is going to give you. Why we need to learn NMR and where we can use this NMR like that. So basically, people will say that organic is the first priority. So people will say that solution NMR is the most used one. But you can also use for solid states, thin film, powder, solid, single crystal, any form you can use it. So there are some major breakthroughs happen over the years from 1946. 1952, the first commercial NMR spectrometer has been designed. 1955, the NOE, nuclear overhauser effect, has been found. And then 1962, first superconducting NMR magnet was established. And 1966, Ernst designed two-dimensional experiments for NMR. So 1969, first conceptual MRI has been established. 1975, first 2D NMR. The first proposed 2D has been completely resolved by experimental technique. So again, 1985, Woodridge applied to protein NMR, protein structures. And then now we have a gigahertz NMR spectrometers available in world. So these two people are the first people who invented this NMR spectroscopy, NMR spectrometer as well. And Richard Hornst is a very, very important person in NMR spectroscopy. He did many development within the NMR spectroscopy. So we cannot forget other people, the contribution from eminent scientists. So I just wanted to thank them for this in this moment. Where we can use this NMR? NMR can be applied on any material, as I told you. Even you can record NMR on gas molecule also. But you need to have that NMR active nuclei. So from physics perspective, you need to understand that from fundamental point of view, how this has been active or inactive. You might have get a question. So we will get you answer in next few minutes. But where this NMR is being used, NMR mainly, as I told you, structural chemistry, basically chemistry, they used this NMR spectrometer extensively. And you can also use for dynamic studies. What is dynamics? Dynamics means when a molecule or a object is in motion, you need to understand the mechanism, what is happening within that system. So that is the dynamics. So you can also use dynamics of molecules, and of course structural prediction, three-dimensional structural prediction being used for protein structure analysis. Again, drugs, medicine, as I already told you. What do you have? You have an atom, you have a molecule. Within the molecule, you have an atom. Within the atom, you have a nucleus. Basically, spins. By detecting that spins, you will be understanding that what system is you have. So there are some limitation of this NMR spectroscopy also. So for a liquid state NMR, you can go up to certain limitation. For solid state NMR, you can go still further. So there are some different comparison between different NMR spectrometers with the electron microscopy and diffraction techniques. Yes, as I told you, NMR is being used by chemistry. Basically, they use the major nuclei is hydrogen and carbon. Why they have used, I'll tell you in a few minutes, because their structural is being built by carbon and hydrogen. So they mainly focus on carbon and proton. So by taking a simple example, from water, you have one oxygen, two hydrogen. So H2O is a composition. But within the atom, you have a nucleus. Within the core of a nucleus, you have protons and neutrons. That will give you the complete information that is going to be used in this case. So what bothering you? Basically, resolution of the particular nuclei and your structural information. We need to start from spin angular momentum and magnetic moment. What is magnetic moment? Any object which possesses a magnetic moment, which has a spin, can give you a magnetic moment. So we need to understand from the spin angular momentum point of view. So angular momentum is being understand from any object. If the object is being rotating, so then it will possess an angular momentum. What type of angular momentum you have? You have 4 different type of angular momentum. One is rotational angular momentum of a molecule and orbital angular momentum of electron, and spin angular momentum of electron and spin angular momentum of nucleus. This is the 4 types of angular momentum you have. And you can see that these objects, means electron is being assumed as an object, neutron, proton, they have a charge and a spin. Electron has a negative charge and spin is 1/2. Neutron has a 0 charge and spin 1/2. Proton has a positive charge with spin 1/2. In compare with the photon has a charge 0 with the spin 1. Let us understand from spin perspective. Spin is an intrinsic concept, intrinsic property. It is a quantum mechanical aspect. Okay, so still The angular momentum, it can be described from the point of angular momentum, and it is a vector quantity. So vector quantity means it has a direction. So for any nucleus within the core of your nucleus, you will have a spins. So you may get a question whether all the nuclei of an elements in the periodic tables can possess this spin. Answer is no. Why? I will show you in few minutes why it is not. Why does not all the elements in the periodic table does not give you spins? But we have a question whether the only when the spin is been there, then only you can detect the NMR by using NMR. So for instance, for time being, you assume that maroon color is a proton configuration and blue color is a neutron configuration. Of course, up and down spins. See, in a proton, that means 1H hydrogen, you have a one proton inside the nucleus, and there is no other neutron. Okay, so you will have only one spin, that is nothing but your 1/2. As I told you, this is a quantum mechanical property. So spin is quantized. That means 1/2 H cross. The energy is quantized. So this spin has a value 1/2. So when it is quantized, you will have some numerical magnitude value. That is what 1/2. Considering in a 2H, 2H is a other form of hydrogen that you can say that isotopes are a different form of hydrogen. It has a one proton, one neutron. So you will have a two entity, but they are not paired. Here pairing can happen within proton proton, neutron neutron. So in 2H nuclei, you will have a 1/2 spins. So that means that it gives you spin quantum number 1. So you can say that first proton and then neutron, and you will have plus plus 1/2 1/2. You will have a 1. Considering C12C6, you have a 6 proton and 6 neutron. 6 means even number. You know that even number means 2, 4, 6, 8, 10, like that. It is called even number. 1, 3, 5, 7, 9 are called odd number. So in this case, you need to understand, you need to keep remembering that even odd means there will be a numbers. Okay, 6 protons are even, 6 neutrons are even again. So both are paired. How they are paired? They are paired like the given configuration, like one downspin, one upspin, one downspin, upspin, like that. It has been paired. So the total spin quantum number should be 1/2 minus 1/2, 1/2 minus 1/2. You will have a 0. And the end of the equation, you will have a 0. The same thing is for neutron as well. So you are at 12C6 has a nuclear spin 0. But we are detecting carbon. That has a different, that is C13 actually. C13 has a 1 proton extra. So you will have a 1/2. One proton, additional proton will have a 1/2. So you will have a neutron will be 0 as remains, and only proton will add that 1/2. So if it is C13, then you will have a 1/2. Spin quantum number is 1/2. Assume that in a boron, so let us take an example. 10 boron 5 has a 5 protons and 5 neutrons. So both are odd numbers. So 5 5s are odd numbers. So you will have a 5 spin configuration like this, given as I given you. The 5 spin configuration will be like this. So you will have a 3/2 3/2. What you have total 6 into 3/2 is a 3. Spin quantum number is 3. So first 2 will be paired and remaining will not be paired. So you will have a total 6 here. 1/2 1/2 1/2 1/2 1/2 1/2. So 6 into 1/2, you will have a 3 here. So spin quantum number for a 10 boron 5 is 3. But 11 boron 5 has a 5 proton, 6 neutron. So you will have a neutron be 0 spin quantum, and then proton will have a 3/2. So you will have a 3/2 spin quantum number. So you can detect with NMR. So this is the as a whole, you understand that your spin quantum number is a major role playing NMR active. We'll conclude it. We can conclude it this way. So this table will give you complete information. So when a proton number is even, a neutron number is even, then you will have a 0 spin quantum number. I have given you some example. You can see that even is 0, and here neutron is even number, that also comes 0. So when you have a odd even, you will have a 1/2 spin quantum number and 3/2. This is based on that how the proton paired, how the neutron paired. So you will have a 3/2 also. So 35 chlorine, 79 bromine, and 127 iodine. These are all will possess a spin quantum number 3/2, and 1H, 19F, 31P are possesses 1/2 spin quantum number. The same thing. Number of proton even, number of neutron odd will give you 1/2 and 5/2. See, this 1/2 has been deduced from 13C, and 17O will give you 5/2 spin quantum number. So when the case of odd means odd number of proton, odd number of neutrons, it will give you 1. So 2H will give you 1, and 14N will give you 1. So I hope you all understand this. See here, when you have a spin quantum number 0, then your NMR is insensitive. For those those isotopes 12C, 16O, 32S will not be detected with NMR. So as I told, I asked one question: do all nuclear elements in the periodic table possess an active spins? No. Answer is no. There is answer is yes also. So you will have some nuclei can possess a spin quantum number. Some will not possess a spin quantum number. So that will give you the idea of how this NMR been used. This is the most fundamental physics actually. So when you want to express any moment, that moment is generated by a spinning of a nuclei, and net magnetization can be obtained from this moment. So that moment is being given by mu I. So mu I is being sum over I the state. That means that you can set to 0 to n, so that you will have a net magnetization M. So this magnetic moment is been described in terms of a gyromagnetic ratio times I. This I is nothing but a spin quantum number. I is what just now we have been seen spin quantum number. Again, this is over ith states. So you will have a average over. So basically you will have a gyromagnetic ratio for a specific nuclei, and that will tell you that the amount of a nuclear magnetic moment, mu I. So over all states, you will have a total M, capital M. So the capital M can also be defined in terms of gyromagnetic ratio times J. J is the net spin angular momentum. Spin angular momentum, you might have read about it. So spin angular, from this, one can express that magnetic field, how influences these torque, or you can say that magnetic moment spinning. So the torque has been defined by dJ by dt. If you know the net spin angular momentum J, then you can definitely define this torque. So again, the reason for a moving object. So that is the torque actually. So this is equal, T is equal to M into B. Here is the catch. The B is what you need. You will have to force the system. System means a nucleus, and the application of a magnetic field is the B. So when you apply a magnetic field, your spin will precise. If you don't apply, your spin will not precise, it will orient in a different orientation of your nucleus. Again, I could tell you that what spin we have discussed, reason for the spin quantum number is completely different, and this spin is completely different. You need to understand that. So you remember that what do you call bambaram? In Tamil it is called bambaram. Torque in English. Okay, so spin top will have a motion. So that motion, only when you tie with the thread and squeeze it, then it will start spin. So that is the case when you are putting into a magnetic field. You are putting your spin into a magnetic field, and your spins will move. So there are two different concepts, so don't mix with them. So again, definitely the spin quantum number is the major aspect that you need to understand. Based on that only, you will be using your spectrometer. So the spin quantum number determinant of I equal to h cross square root of I into I plus 1. This is a nuclear spin vector. This is when you are putting into a magnetic field, your energy states will be determined. So that is determined by EI equal to B into I plus 1. So I is nothing but a spin quantum number, as I already told you. For all other axes, they are 0, because magnetic field can be only applied on only one direction, either in a Z direction or Y direction or X direction. So we consider that Z direction. Z direction is the laboratory axis direction. So I is equal to h cross mi. So that mi is the azimuthal quantum number, which gives you the number of states can be availed, and where you can manipulate your spins between them, and then you can get your data. You can get your information actually. As I told you, they are quantum mechanical states. They are quantized. So that means that like a plus I to minus I, it will be kind of an increasing order, one at a step, not in a complete jump. So if assume that you have a 1H is a normally a hydrogen. People in chemistry, people called that a proton. So if I tell you some proton means that it is nothing but a hydrogen, 1H. Okay, so don't mistake me, because there are some terminology that you really need to understand from chemistry point of view, because they are the major user. So from their point of view, you need to understand. So it's become a colloquial language in NMR. So 1H means proton. Actually, it is a hydrogen. So it has a spin quantum number 1/2. So that when you put into a magnetic field, so this quantum levels are generated. This is nothing but your azimuthal quantum number, 2j plus 1 values. So you just add 1 to 1 with plus 1, 1/2, then you will get a minus 1/2 and plus 1/2. So you will have a 1 unit in between them. So this is the degeneracy happened within the nucleus. So this particular process is called a Zeeman effect in physics. People call that a Zeeman effect. Okay, so you can also say that a perturbation is happening. So how you perturb your nuclear structure, nuclear energy levels. This is how you can perturb. So if you put off your magnetic field, your perturbation will be 0. When you put on the magnetic field, your perturbation is happening. Then you will have a 2j plus 1 energy levels are splitted. The highest energy state, that is the excited state, is called beta state. Normally, this is called a beta state. People in physics, they call excited state. In NMR, it is labeled as a beta state, and the ground state is called alpha state. So m equal to plus 1/2 is an alpha state. M is equal to minus 1/2 is a beta state. So your spin will precise based on your dipole moment mu. Okay, so once this moment, the motion is being set up, then you will have a one particular frequency. So that frequency is called a Lama frequency. This is very, very fundamental in NMR. Lama frequency is been defined by omega 0 equal to gyromagnetic ratio times B0. That means assume that you are having a 100 megahertz magnet. Then you will have a energy splitting. You have a 400 megahertz. You are jumping from 100 megahertz to 400 megahertz. What will happen? The splitting will be multiplied by 4 times. The splitting will be, the gap will be increased by 4 times because your magnetic field strength is increased to a 400 megahertz. So your Lama frequency will be based on this magnetic field. You see that omega 0 equal to gyromagnetic ratio times B0. Gyromagnetic ratio is an property of nucleus. It will be fixed for a particular nuclei. It will not change within the nuclei itself. It is fixed for a specific nuclei. So as I told you, what is Zeeman interaction? Zeeman interaction is when you switch off your magnetic field, your spin will be oriented into different orientation or axis. But when you switch off a magnetic field, what will happen? All spins will be aligned to along the magnetic field. Either it can be an up spin or it can be a down spin. It should be aligned to a external applied magnetic field. This is called laboratory frame. All the spins will be aligned. This aligning is called Zeeman interaction, or you can say that in quantum mechanical term, you can say that perturbation. So it is happening within the quantum states. Then your spin nuclei will be populated between the states. As I told you, you have a quantum number, spin quantum number. Based on the spin quantum number, you will have a 2j plus 1 values. So if it is 1 by 2, I equal to 1 by 2, you will have a 2 state. If it is I is equal to 1, you will have a 3 states, 0 and 1. I already told you it increases in terms of 1, units of 1. That means 1 H cross. H cross is the quantized energy state. If you don't put H cross, this is by default, you need to understand that. So if you don't put H cross, then it is not quantized energy state. This is a quantized energy state. This is a 1 H cross and this is a 1 H cross again. Again, I is equal to 3 by 2, you will have a minus 3 by 2, minus 1 by 2, plus 3, 1 by 2, plus 3 by 2. Again, for I is equal to 5 by 2, you will have a minus 5 by 2, minus 3 by 2, minus 1 by 2, plus 1 by 2, plus 3 by 2, plus 5 by 2. So your transition will happen between these states. The red lines, the red dotted lines, the arrow mark will indicate you that the nuclear population can happen between these states. That means, in simpler term, you might have attended different talks. People might have explained you how this electromagnetic radiation is being excited and emitted, like that. So this is a kind of a excitation happened within the nuclear states by using radio frequency. So that we will do it. That we will see in later hour. You will understand that how it happens, so why it is give you multiple peaks like that. I'll explain to you most of them. This is the most fundamental physics, how this quantum states been utilized in this NMR spectrometer. Okay, I already explained this. I guess the alpha state and beta state. Alpha state is the ground state and beta state is the excited state. And again, you will have a energy which has been dependent by this magnetic field. So spin energy states also I already explained how the spin is possessing a moment. So if you have any doubts, this is a fundamental. So when you have a transition between alpha state to beta state, some nuclei is being transferred from ground state to excited state, from excited to ground state, then you will see that there will be a resonance is happening. That resonance is nothing but a nu. This resonance is nothing but nu. So yeah, this is what I already just now I told you. What is ground state, what is excited state, how this excitation is happening. Yeah, based on our understanding, until now we have seen that spin quantum number is a major major entity which decides that whether the nuclei is NMR active or not. Here, there are some atoms, they don't possess spin action. They are NMR inactive atoms. So all other atoms are classified like a spin off integer quadrupole spin and spin 1. So within these three category, you can classify them. So mostly spin off is the most easiest thing ever you can do. The most toughest thing is quadrupolar nuclei. Spin 1 and half integer quadrupolar spins are called quadrupolar nuclei. Both are quadrupolar nuclei. They are the most toughest thing. That end of the talk, end of today, you will understand that what this quadrupolar nuclei and what they are doing. So to take that from initial point, this is the simplest table which relates with nuclei and gyromagnetic ratio and abundance. You see that a proton has a high abundance, 99%. So your spin is already 1/2. So you will have a highly detected nuclei. Okay, you see carbon is only 1% of natural abundance. Again, your gyromagnetic ratio is very, very low compared with 1H. Means your sensitivity is been degrading. So same thing is for nitrogen. You see that very, very small one value, natural abundance, and very, very small value for and again negative value for gyromagnetic ratio. You see that phosphorus, you will have 100% natural abundance. That means that you can see the signal very quickly, and your gyromagnetic ratio also in a positive direction. So people have concluded, they made an attempt and concluded all the nuclei, what is the sensitivity, what is the spin, quantum number, and what is the natural abundance. All of them they're tabulated. So basically, I want to talk about this sensitivity because most of the experiments within the NMR is being developed because of this sensitivity, addressing this sensitivity. Means you have a nuclei in the ground state and they are going to excited state. You should get a signal, but it is not happening as you expected. It is not that simpler case. If it is spin 1/2, it is very simple, you get a signal. If it is spin quadrupolar nuclei, then you will have a hurdles and you need to solve them. By understanding the factor which affect the sensitivity is a major role. That's why the new instrument is already been developing in order to address this sensitivity issue. Okay, so here sensitivity is a factor that is actually proportional to delta n. Delta n is nothing but ground state to excited state. The ratio between ground state to excited state actually. This is alpha and this is beta. You can say that some number is missing. Something is missing here. It's okay. This delta E again, it's a energy. This is already related to magnetic field. If you go high magnetic field, you will have a good sensitivity. If you go low magnetic field, you will have a less sensitivity. So the magnetic field also play a major role, and it's an exponential quantity. To tell you that to introduce you NMR spectrometer, what is NMR spectrometer? You assume that a small magnet, horseshoe magnet. So this is a north pole and south pole. You assume that this is a horseshoe magnet, and you assume that this is an electromagnet also. You can assume anything, but it will give you some polarity, and within the polarity you will have a sample and you will have a coil. Okay, so one, it should generate a radio frequency pulse and it should apply to the sample, and one, it should receive the signal from the sample and it should record as a spectrum. Very simple mechanism. But you have one item is containing this sample, one is magnet, another one is console. So you have a magnet, probe, console, and a computer. Finally, user interface is nothing but a computer. What you get? Basically, Fourier transform of frequency. Fourier transformed frequency of a NMR spectra. So that is what you are basically getting. So I'll explain you this in detail after I introduce you what is a spectrometer and how it works. Okay. So there are several NMR spectrometers are available in the market other than Bruker, other than Q-Antec. Two spectrometers I didn't include here. As one is Bruker, well-known one. Everybody is using the Bruker machine, and Q-Antec, that is really new one from China. People are not interested, so I just didn't put in this slide. So you will have other spectrometers like a quad NMR spectrometer, and SpinSolve is there, and Geol is there, and Agilent NMR spectrometer is there, RS2D spectrometer is there, and HTS110 spectrometer is there. That is a purely cryogenic free NMR spectrometer. All other spectrometers are superconducting magnets, but HTS110 is a completely cryogenic free. So when you just put on a magnet and then switch off, something like that, you can use it like a mixie and a grinder, something like that. But superconducting magnets are not like that. So this is a one example of actual superconducting magnet. It should be a tall magnet, like a similar, equivalent to my height. I would say 7 feet or something. So inside the magnet, you are seeing a wounded coil. This is a wounded coil, and you can see that other picture also. This is a single coil which has a length of 305 kilometers. So this is a technique that they use to wound the coil, and this is a superconducting coil. When this superconducting coil is immersed in a liquid helium, then they charge with current, high current, then you will generate a magnetic field. So that I'll explain you in a few minutes. But before going to that, I wanted to explain you the complete schematic of this console. What is console? What do you need for a NMR? From console, you need to generate a radio frequency pulse, RF pulse. You see here, RF controller is there. So one is you need to have a synthesizer. Synthesizer will generate a radio frequency pulse, and that will be transmitted through linear transmitter, and then it will be amplified. Amplified means if I produce 1 volt, it should be amplified with 5 watt or 100 watts or 300 watts, something like that. So amplifying is happened with this linear amplifier, and then it will go to that preamplifier. Preamplifier is where actually what type of pulse we are putting, and is it really necessary pulses we are sending. That is what decided, checked, verified, double checked, something like that. Preamplifier will do, and then it will go to probe. This probe will be inside this magnet actually. Within the probe, I'm going to explain you in detail of understanding how this NMR probe has been designed and developed. I will explain you solid state, liquid state also. But as of now, you assume that a probe is the one where your quantum mechanical states are manipulated. That is the only thing you understand now. Okay, so through this preamplifier, it will go and apply this radio frequency pulse, and a small signal generated within the sample molecule is being received from the same probe, and then it is again give back to preamplifier, and then it will go to quadrature detection. This quadrature detection will reduce the noise and try to boost your signal strength. You will understand the end of this talk what is noise and what is signal, because that is what the actual objective of this talk. So this quadrature detection will boost your actual signal, real signal. You can say that no fake signal will be detected. So this is ensured here within this quadrature detector, and it will be given to ADC, analog to digital converter. From here to digital filter, and then from digital filter to, it's a simple filter, simple filter, RF filter. You can say that a capacitor inductor network. From that it will go to computer. This computer will store this data which is analyzed by this ADC, and it will be stored in a text file. That data will be having a information of time domain data, simple time domain amplitude data will be there. I'll explain you. You see here, this is the actual data, raw data. You can say that when I apply a pulse, what happened when I apply a magnetic field, when I put the sample into the magnet, what will happen? All the spins will be spinning like this. The top figure like this, all the spins will be spin like this. All NMR active nuclear spins will be positioned like this. Again, you have showed me some quantum mechanical states, sir. What is this? You are showing some arrow mark. What is this? I don't get correlated. See, this is actually what is happening within the sample itself, real time, real objects. But what I told you is the quantum mechanical thing, that you need to visualize yourself in a quantum states. So here is the excited spins, and when RF pulse comes, what happen? All the spins will not be in the Z axis, because your magnetic field is in the B0 axis. This will not be in the B axis. It will be in the transverse plane. This transverse plane initially will receive very high intense signal. That is what you are getting, a very high intensity here. These spins are precising. That means they are liberating some energy. That means that this spinning will lose its intensity. So that is what your intensity is, keep on decaying up to certain time. So initially it will be high, finally it will be very low. So this is called free induced decay. This is called free induced decay, FID. FID is the what? Raw data. You just implement some Fourier transform mathematical function, then you will see that a frequency. This is a time domain data. 1 over by t equal f is equal to 1 over by t. You know that. So you simply from Fourier transform you will get a frequency. This is a frequency. Frequency will give you that what actually you had within the molecule. So if it is showing only one signal, then you will have only one environment, only one unique environment within the sample. That is what your frequency is. See, now I'm saying frequency. After some time, I would be saying a chemical shift. Chemical shift means this instrument is calibrated, and with respect to some known frequency, that is called omega ref. Omega ref is known nuclei with a known frequency, so that what I'm getting is a real signal with a particular ppm value. So this should be in a part per million ppm value. Okay, so yeah, I explained about this console, what console is doing actually. Okay, so all other parts are additional thing. You don't need additional thing now. As of now you focus on what is NMR, why I want to use NMR, where I want to use NMR. That's it. If you understand this, that level, that is okay for us, at least now, to the beginner level. So now I'm going to explain about this NMR magnet. What is NMR magnet? Magnet has a 3 assembly. One is coil assembly, that is the innermost assembly. Another one is liquid helium assembly. Another one is liquid nitrogen assembly. Another one is vacuum. So you will have 3 different assemblies. How they are? Let me explain you. This is actually nitrogen vessel. You assume that a nitrogen vessel, a complete magnet has a vacuum ensemble, I would say. Complete vacuum ensemble. Outer diwar is a complete vacuum ensemble, and then you will have a nitrogen diwar. In order to keep your nitrogen for a longer time, you need to have a vacuum environment. So that's why this cylindrical shape, this will be kind of a circular shape. So you pour nitrogen here, and it will stay for some time, at least 1 week. And you will have a helium vessel. Helium vessel also will have a cylindrical shape, and you pour here this helium, and you place a superconducting coil. I told you, that's a 300-meter long superconducting coil has been wounded, and they kept inside this helium bath. So our ultimate aim is to keep this superconducting coil under this superconducting state. Then only you can continuously generate a magnetic field. So you know that Bose-Einstein equation, Bose-Einstein phenomena. Because of that, you will get a zero energy loss. You will get continuous motion of current will produce this electromagnetic field. So by charging this coil, you will produce a continuous magnetic field. This will last longer until you keep this helium top up every 4 months, every 5 months, and every week you need to top up the nitrogen in this vessel. And then you will have a room temperature shim. I'll tell you what is a room temperature shim means. It is a simple electromagnet. Simple electromagnet means few hundred tons of coil will be wounded on top of this magnet, just like this type of shape. Okay, so from bottom and top you put this coil, and then you will apply additional magnet. You will create additional magnetic field. You apply current, and then you create additional magnetic field. That additional magnetic field will reduce any inhomogeneity within the sample. What is inhomogeneity? I'll explain you. Inhomogeneity means where you have a perfect hypothetical lines will be disturbed is called inhomogeneity. Homogeneous means lines are in a parallel manner. You assume that the electromagnetic radiation, they are 100% parallel manner. When you put some object which disturb the electromagnetic radiation, will produce you inhomogeneity. So what you need again? You need a probe. Probe has to be put it into the magnet, and then you need to put a sample into that, and then you need a radio frequency coil to be excite the sample, and you will get a signal. I hope you understand what is mean by NMR spectrometer and NMR magnet now. Now we will understand how many number of probes are there, why the probes are being developed, why these probes been you can say that n number of probes are developed. They are basically to enhance the sensitivity of insensitive nuclei. So carbon, as I already told you, based on sensitivity and gyromagnetic radiation, the nuclei may not be detected quickly. You need to run for a longer time, like 1 day, 2 days, 3 days, sometime 1 week or so. So number of probes are being developed in order to get a enhanced resolution of NMR spectra. There are case by case problems are there. We will go one by one. Case by case means each individual problem is being identified individually, independently, each independent labs. So you can say that even in a liquid state also you will have a problem. Even in a solid state you will have a definitely problem. Okay, so there are like numerous solid state probes are there, numerous liquid state probes are there. They are specifically meant for either 2-channel detection, 3-channel detection, or 4-channel detection, or multi-channel detection. They meant to enhance the sensitivity of your nuclei. Basically what you need to get a signal, well resolved signal. That is what you need. You should not get any fake result. Fake result means any artifacts should not be detected from the probe. So you see here some probe assemblies that are there. It's a very complicated structure you can see now. So what you have is you have a inner coil and outer coil. 2 coil is there. So this is one thing you can take now. If I tell you 2-channel spectrometer, then you can only use 2-channel. If I tell you 3-channel spectrometer, then you can do 3D experiments. 2D experiments can be done with the 2 coil. 1 coil, you can do only 1 experiment. Okay, so here they use a 2H also. So channel means you can say that you see this 1H is there. So that means that this is a 1 channel. And BB is a broadband. Broadband means you can tune your frequency from 50 megahertz to 100 megahertz or 200 megahertz. But your 1H frequency is set to specific nuclei. Can anyone tell why? Can anyone tell why?
Participants interact with the resource person. Unable to answer, at least I don't know what convey pannolla. Aruna Devi, any answer?
So no, sir, I didn't have any idea about it, sir.
Okay, so good. I appreciate you. See, you have a spin quantum number. Assume that you have a spin quantum number 1/2. So that means that you will have only 2 energy state. I'll take this as a simplest example. No complex examples. Okay, you will have a spin quantum number 1/2, and your energy levels are only 2 energy levels. One is the excited state, one is ground state. That's it. Okay, your frequency is, I already told you what is a Lama frequency. Lama frequency is fixed now. Okay, so based on this energy gap, your Lama frequency is fixed. You see this E is a fixed. So your nu is fixed now. Means proton frequency is fixed. Always proton frequency is set as a reference frequency. All other nuclear frequencies were calculated from the proton frequency, because this is what the simplest and easily detected nuclear. So people set this proton as a reference frequency. So my question is, why this proton is being set as a frequency, and then this broadband has been taken as a tuned frequency. So you have a one specific dedicated channel which is fixed nuclei, and that will be fixed for specific spectrometer. If it is a 300 megahertz spectrometer, this resonance will be 300.13 megahertz. That will be fixed. Then all other nuclei will be calculated based on this proton. So now you will have some scaling. You have a ruler, no? You have a ruler. You have some scale, something like that. So these other frequencies are calculated based on proton, and then this BB can be tuned accordingly. If I want to tune phosphorus, if I want to tune aluminum, if I want to do carbon, I can tune them, but it should be low frequency region. It should be low frequency region compared with the proton frequency. Always proton frequency is the highest frequency. You remember this table actually. This is the table. You need to remember this. You see proton is 75 megahertz and proton is 300 megahertz. So that means that the spectrometer frequency B0 is set to 300, means this should be 75 megahertz. If this is set to 400 megahertz, then you will have 100 megahertz here. So your relative frequency will be calculated accordingly. All other nuclei will go according to that way. So okay, you have a inner glass divar is there to protect the gold coil, and then outer glass divar is there that also protect the outer coil. So you, as I told you, two coils are there. One is inner coil, another one is outer coil. So you will have a protection for that, those coils as well. So other than simplest probe, there are gradient probes are available. What is gradient? Gradient, the name itself tells you that something is different with respect to position. So that means that you have a additional coil will be placed around this probe, and this coil, using this coil, you can also set a magnetic field. Magnetic field means some electromagnetic field, additional electromagnetic field can be set from the radio frequency pulses. So that is called the gradient probe. So by using additional gradient, you can enhance this signal actually. So end of the day, you will get a free induced decay, and then Fourier transform them, and then analyze those data. But how I get this quickly? So that's why this gradient probe has been invented. Very basic structure of the coil is the saddle coil. The saddle coil means this structure. You see that from here, this line is going, and this going this way, and it is coming this way, and then it is turning this way and coming this way, and it is end up here. So this means that between these two, you will have a tuning capacitor, and then it will apply the radio frequency pulse also. So this is this arrangement is called a saddle coil. Most of the liquid state probe, you will see this structure of the coil. What it is, how it has been used. Here is the question: whether my probe is tuned to particular frequency or not. How I can know that the frequency is being set up? I told you one time that we are using preamplifier. By using the preamplifier, you can check the tuning of the probe. That means you will have a simplest circuit like this. This is the simplest NMR probe circuit, and you have an inductor. This is a coil, and you have a tuning capacitor 1 C1 C2. By using this C1 C2, you can tune the probe to a particular frequency. If I want to tune to 400 megahertz, I can tune to 400 megahertz. If I want to tune to 300 megahertz, I can tune this dip to 300 megahertz. If I want to tune to 100 megahertz, I can tune this dip to 100 megahertz. So that means that the delta omega to the omega will tell you that the quality factor of the coil, because you see that one is a tuning, one is a matching capacitor. Basically, nu zero equal to 1 over by 2 pi square root of LC. That is what the resonance frequency of this simplest network, circuit network. This is a simple circuit. So this based on this inductance of this coil and the capacitance of this coil within the circuit, this resonance frequency is set in such a way that to get a good quality factor. If you get a high quality factor, then your probe sensitivity will be very, very high. If you get a low quality factor, then your probe sensitivity is very, very poor. You will not see a signal even 1 week or 1 month if you run NMR experiments. So sensitivity is a factor that depends on directly proportional to Q. The Q is equal to omega 0 divided by delta omega. All other parameters are known values, so we don't need to worry about them. So as I already told you, very simplest single tuned coil is this structure, and what you need a capacitor. One is a coaxial cable and variable capacitor, like a chip type capacitor, and then coil. So if you have them, you can definitely make a probe. So this structure is a double resonance structure. What is the double resonance? What is a single resonance? Single resonance is you can only tune to one particular frequency. You cannot do multiple experiments. As I already told you, only one channel will be available. Only one channel will be allowed to use. But in this case, you have a two channel. You see, one is H here, one is X here. So that means that one proton frequency you can set, one X frequency you can set. This I can set it to carbon, this I can set it to proton, this I can set it to, sorry, not proton, phosphorus, this I can set it to fluorine, this I can set it to lithium, this I can set it to aluminum, anything.